Hi, hi to everybody. I hope you are well wherever you are. Now today's lecture is about the Bohr model, which is section 6.5 in our prescribed textbook. As you can recall, we have dealt with two different atomic model, which was the Thomson model, and others are calling it Plum-Pudding model, and we have also done with the Rutherford model. Now today's lecture is about the Bohr model. Now, Niels Bohr in 1913 suggested that the atom resembles a small planetary model. Now, from these suggestions, I want us to consider atoms as a planetary model. For an example, when you look at this image here, this is an atom and you've got an electrons from the Rutherford. You remember, Rutherford suggested that the electrons are surrounding the nucleus. Now, in this case, your center is the same as the sun, and the electron is the same as the planets which are orbiting around the sun. So in this case of an atom, I want you to see the fact that there will be an attractive force because of there will be attractive force, the Coulomb's attractive force, because of the negative electron and the positive nucleus. And what I also want you to see is the fact that the velocity of this electron while it is circulating the nucleus is always tangent to this radius r, which means r and v are always perpendicular to each other, because this velocity, when it's here, it will just be pointing at this direction, and the angle between r and v is always 90 degree. Now I want us to use the Coulomb's law and the Newton's second law. If you use the Coulomb's law and second law, this is what you are going to have, because now this Coulomb's law must just be equals to the centripetal force, which makes this electron to move in the circular orbit. So this is what you are going to have. That force, the Coulomb force, must just be equal to the centripetal force. Now I just want to work out the last two terms of this equation, so that I can derive the kinetic energy for you, so that whenever I want to calculate the total energy, which is the potential plus kinetic energy, you can always remember that the kinetic energy is given by that term. So now 1 over 4 pi, that force is 1 over 4 pi epsilon naught E squared divided by R squared is equals to the centripetal force mv squared divided by R. So now in this case, I think you will agree with me that this R will cancel one there. And now I want to multiply this time by a factor of half, and I multiply by a factor of half this side. So what will this equation look like now? This equation will be 1 over 8 pi epsilon naught E squared R, not R squared, R is equals to 1 over 2 v squared. And this term here, this term looks familiar to us, and that is nothing else but it is equivalent to the kinetic energy. So as a result, the kinetic energy therefore will just be defined in terms of this equation here. Right, now let us also talk about the potential energy. The potential energy U, because for you to get the potential energy, you need two charges. It's either positive, both positive, or both negative, or either one of them is positive or negative. So now in that case, the potential from your first day, we define the potential as 1 over 4 pi epsilon naught E squared divided by R. That was your potential energy. So now in that case, if you want the total energy of the system is just going to be the kinetic plus the potential energy. That will be your total energy. And this is what you are going to see. Now the total energy is just given by this. So now these are like terms, and here is negative. The potential here is negative just because there is a negative electron and a positive electron. Now if you put it into the equation of the potential, obviously you will have a negative sign here. So as a result, this is a like term and this is a like term to this. Now if you work out, if you minus this to that, you are just going to have a negative here. So the answer for the total energy is just given by this term. Is just negative this term here. All right, good. Right. However, I must also state that when we consider the classical electromagnetic theory, the planetary model is doomed. It doesn't apply because an accelerated electric charge radiates energy or electromagnetic radiation, which means that total energy must decrease, radius must decrease. As this electrons loses energy, that radius must decrease up to when this electron crashes with the nucleus. This is what the classical theory is actually telling us. However, physics had reached a turning point in early 19th century with Planck's hypothesis of the quantum behavior of radiation. Now, the Bohr models of a hydrogen atom, for an example, we are dealing with a hydrogen atom because this is just the simplest an element that we can deal with because it's got only one electron. So now the Bohr general assumptions are as follows. Number one, stationary states or orbits must exist in atoms. Orbiting electrons do not radiate energy in these orbits. These orbits or stationary states are of a fixed, definite energy E. For an example, if they radiate energy, of course they will lose energy, and we will find the electron crashing to the nucleus, and that is based on the classical theory. But the Bohr assumption is the fact that in the stationary state, those electrons are not radiating any energy. Now, the second assumption is the fact that the emission or absorption of electromagnetic radiation can occur only in conjunction with a transition between two stationary states. The frequency f of this radiation is proportional to the difference in energy of the two stationary states, which are just given by this equation here. And I'm sure that you still remember this equation here, that equation where you have hf, and h is the Planck's constant and the f is the frequency. It can just be written in terms of the Planck's constant c divided by lambda, because the frequency is defined in terms of this. So now, in case you don't know the frequency, you know the wavelength, then you can just play with, when you know the frequency, you can just use this one. So that's what I also wanted to remind you. So where h is nothing else but it's just the Planck's constant. For an example, from the energy 1 to energy 2, you see, this electron will lose energy and goes to that lower energy, and when it absorbs energy, it can go to the higher state or higher energy level. Now, the third assumptions of Bohr is a classical law of physics do not apply to transitions between stationary states. So the classical laws do not apply from this transition to this, or from this transition to the other transition. The classical laws do not apply, because otherwise the classical law we have actually seen that the electron will radiate energy and it will end up colliding with the nucleus, and that is not the case. That is not what we are seeing, because the atom is not going to crash. Up. Now, the last Bohr assumption is the fact that the mean kinetic energy of the electron nuclear system is kinetic energy is just given by this equation, where the f orbit is the frequency of the rotation. This is equivalent to the angular momentum of a stationary state to be an integral multiple of the h bar, the multiple of h bar. Remember, good people, this can be defined in terms of the h bar, multiple of h bar, which means you can have 1 h bar, 2 h bar, 3 h bar, and so on. You can't have the half h bar or 3.5 h bar. So you will have a multiple of h bar. So now, in this stationary state, the angular momentum of the electron may have a magnitude of, as I've just said now, the magnitude of h bar, 2 h bar, and then you might have 3 h bar, and so on. But you might never have 2.5 h bar or 3.1 h bar. This is what we call the quantization of the angular momentum. Angular momentum is quantized. So that's what you will normally hear from now onwards. The angular momentum is quantized. It means that you will only have the multiple of the h bar. Now, as we have seen that the position vector r that locates the electron relative to the nucleus is always perpendicular to the linear momentum. As we have seen that the r is always perpendicular to the velocity, and the velocity it's I mean, if the velocity is within this momentum. Now, as a result, the magnitude of this L cross R, I just want to remind you about the vectors, that the angular momentum vector is just given by R cross P. But I want to write this S cross MV. But R and V are perpendicular to each other. And I also want to remind you that vector A cross vector B is nothing else but is magnitude of vector A times the magnitude of vector B, the sine of an angle, say an angle theta between them. And what is also important is the fact that I want to remind you the sine graph. The sine graph can be plotted in this fashion. So where here is 2 pi, and then here you've got pi, and then here you've got pi half, and then here you've got 3 pi halves. So now if this vector is perpendicular to this vector, it means it's got 90 degrees, and then sine of 90 is just 1. Now, as a result, I hope you can agree with me that I therefore can write the magnitude of the angular momentum L, the L without a vector sign, because it's just the magnitude, is just going to be given as R mv. So this is what you are seeing here, that the angular momentum is just given by that equation over there, right? So now Bohr's postulate is that the angular momentum is quantized. You are only going to have the multiple of h bar, where n is an integer. It can be 1, 2, 3. It cannot be 1.5 or 2.5 and so on. So m is the angular momentum is quantized. Right. Now, from this equation here of the angular momentum, I want you to make V a subject of the formula. Now, from that equation here of the angular momentum is quantized in h bar. And you remember that h bar is nothing else but, in terms of the Planck's constant, is just this. In terms of the Planck's constant is just this. But normally, in quantum mechanics, because we are in h bar scale, we normally use the h bar instead of this Planck's constant. Now, from that equation of the angular momentum, I want you to make the velocity a subject of the formula. If you make the velocity of a subject of the formula, this is what you are going to have, mr. Now you take this, you plug it into the equation of the kinetic energy. So now if you do that, if you plug that to the equation of the kinetic energy, you will agree with me that this is what you are going to have. This is what you are going to have, because the velocity from this equation is this. Then you are just going to have this as your kinetic energy. As I've already derived from you previously, that the kinetic energy is just given by this equation there. Now, to find a series of allowed values of the radius r, therefore, in this case, you make r a subject of the formula. If you make r a subject of the formula from this, because this mass will go away, and then you will only have one mass there. So as a result, if you work out this is what you are going to have for your radius or allowed r. You cannot have the values of the radius orbits everywhere, but that values of r will depend on this n, on this quanta of angular momentum. All right. Now, where this equation can be written in terms of this, where this n2 is just this, and then a0 is nothing else but is what we call the Bohr radius, is defined as this. And when you put the values there, you can just see that the Bohr radius is nothing else but is this value. 0.1 it's roughly 0.1 nanometer, right? Now the smallest diameter, because now we know the radius, we know the radius R. The radius is just given by this. Therefore, for hydrogen atom, therefore we can be able to determine what is the diameter. The diameter must be twice the radius. Now the diameter is just given by twice the R1. Now I also want to go back to this equation here to just show you that now, I mean, if n is equals to 1, this term here will just be 1, and then I'm just going to have A naught. I'm just going to have A naught, and then the A naught is just given by this equation here. Now in that case, the diameter is 2R1 or 2A naught, because R1 is just A naught. So now this is what you are going to have. I mean, roughly the diameter of the hydrogen atom is 0.1 nanometer. 0.1 nanometer. Right. Now N1 gives its lowest energy state, called the ground state. Now the energy of the stationary states are found by substituting the R, the equation 6.28, equation 6.28, which is R, to that equation of the energy. You remember the equation of energy is got, the equation of the total energy is got R, but this one is kinetic energy. Remember the total energy, the kinetic energy plus potential energy, it gives us the -1/4 pi epsilon naught this. Now you've got R. Now if you want to get En, you just substitute this into that equation of energy, not this one, of the energy, which is equation 6.25. Now you are just going to have this equation as your energy, right? So I hope you are able to see that. Now, I mean, if you don't see these things, please just write them down. I also want to show you that En, in some books, they normally write it as E naught divided by n squared, where E naught is nothing else but it's just -13.60 electron volts. And I hope you still remember where this negative come from. This negative come from the fact that when we add the kinetic plus the potential energy, we had this negative sign there. So that's where it is actually coming from, right? So that's what you are going to have for your energies of that stationary state. For an example, if n is equals to 1, therefore you are just going to have n is equals to 1, then you are just going to have this value, because this one is 1 squared, is nothing else. You are just going to have this value. That is what your E1, right? Now for n is equals to 2, if you punch this number divided by 4, 2 squared is 4. This is what you are going to have, and so on. So that's what you used to see on your hydrogen spectra. The values of the energy are starting from the energy, which means the energy goes the energy goes up in this. The energy goes like this. I mean, from negative value to the 0. And I'm sure you also understand that y at energy at E infinity is equals to 0. That is very simple to just denote. For an example, if you have a fraction, for an example, as I've told you that the En in some other books, En is just defined in terms of E naught divided by n squared. So now if this value becomes too big, where E naught is nothing else but E naught is 13.60. So now if you have this value divided by a very huge number where n goes to infinity, this will roughly goes to 0. So that's why the En at infinity, that's why En at infinity is nothing else but it's just En at infinity, is nothing else but it's just defined as 0. So that's what you are going to have for the equation of the energies for those stationary state. Now the Excitation energy of an excited state N is the energy above the ground state. For an example, En minus E1. Thus, the first excited state, N is equals to 2, has excitation energy given by this. So now it must be E2 minus E1. We know what is E2 for hydrogen atom. For an example, if you go back, E2 is this value minus this one. So that's why you are just going to have this value here. This value as your E2, and then your E1, we know what is the E1 is. E1 is given by this value. So now the excitation energy from E2 to E1 is just given by this value, 10.20 electron volts. And for example, the excitation energy, the energy difference between this states, this N1 and N2, the excitation energy here is just given by this. And we also, for a second state, the energy 3 to E3 from here, from this energy state to that state, is just E3 minus E1. And the excitation energy is that energy which will just be from this value there to here. That will be equivalent to 12.09 electron volts. So that is the excitation energy. Now, the other important thing that I want you to know is the fact that the magnitude of an electron's energy, the magnitude of an electron's energy is sometimes what we call the binding energy. For an example, the binding energy of an electron in the N is equals to 2 state is just given by the magnitude, of course. The magnitude. You don't have a negative because I'm just talking about the magnitude. It's just given by this. By this value. That is the binding energy of an electron in that state. So that means now if the electron can get this energy, it will actually move off. That electron will become free electron. It will move out of an atom, and that atom will become an ion because the electron has moved off of that atom. Right. Now, if the electron jumps from N is equal to 1 to N is equal to 2, photons appear with energy. As I've already said, that the photon will appear with this energy. Now, if this jumps from one state to the other, the photon, for an example, if it jumps from this state to the other state, the photon is absorbed. So now it can absorb a photon, so that the difference between these two energy levels is just given as the energy of that photon. All right. So now in that case, because we know what is the energy, now if we use that equation of the energy, because we know what is the equation of energy, and then we for N1 and N2, this is what we are going to have. And in this case, for the frequency, we are just going to have this. Now, I also want to remind you of the fact that, you see, in this case, you have HF. You have HF is equal to En1 minus En2. Right. Now, I want you to write this in terms of the multiple of the H bar. So now, from the fact that H bar is just equal to this divided by 2 pi, it means that H bar, instead of me writing the H bar here, I can just write what we call, I can just write the multiple of 2 pi H bar, and then the frequency, and then this term here, it will come here. Right, from there, you know what is the energy, and then you will divide by 2 pi, by the 2 pi H bar. So now this is what you are going to have if you do that. Now that is why in that equation you don't see this Planck constant, but you are seeing the H bar. So that is why now that factor there, it has actually grown up to 64. So that's what you are going to have. So note that this is H bar, this is not H bar. All right, good. So the frequency will just be defined in terms of that equation. Now the wavelength of the emitted radiation is just given by this equation now. Now this is what we know from our first year, but now we know what is the frequency. We can just put the frequency in there, and then this is what we are going to have for the equation of the wavelength. And now we can actually chop it down by using the Reinberg constant, which is nothing else but this R subscript to infinity is what we call the Reinberg constant. Now if we use that, this is what you are going to have as your wavelength. All right, good. Now the value for the Reinberg constant is just given by this. So now you only need to know from which state to which state, so that you can be able to determine what is the wavelength that is required by that state. Now, for an example, let us just do this example 6.7. Find the wavelength of the transition from N1 is equals to the N1 is equals to 3 to N2 is equals to 2. And from, that's the first question. And the second question is from N1 is equals to 4 to N2 is equals to 2 in atomic hydrogen. Now, you are just going to use that equation that we have derived now, and then from there you know what is this. This is the inverse of the Reinberg constant. Now you know what is N1, you know what is N2. N1 is this one and N2 is this one. Now for the first one, this is what you are going to have if you plug the values, and this is actually in the visible range, and I think it is in red region of the electromagnetic spectra, or of the visible spectra. Right, now for the other part of the equation, so now this is what you are going to have if you plug the values, and this is in the blue region of the visible region of the electromagnetic spectra. Yes, because roughly the visible region starts from 400 to say 700, for argument's sake, nanometer. So now this is for the visible region of the electromagnetic spectra. So all those wavelengths are actually going to be seen by the naked eye. We are going to be able to see different colors that are going to be emitted by this hydrogen atom. In fact, maybe that is one of the reasons why you are seeing the different colors of a hydrogen when it's being excited. The hydrogen gas tube is excited in your experiments. That's what you are going to see. I mean, the red, this is red region, and this is the blue region of the visible visible region. Now let us also talk about, for a nucleus of charges, when the atoms Z is greater than 1, because we are just focusing on the hydrogen. Now we also want to focus on the other elements, for example, helium, boron, and you name them. So now in that case, the Coulomb force for that is just the same as that one, but here you just multiply by the Z, which is that the Z, which is the atomic number of that particular atom. So for the allowed radii, you just multiply the charge by the Z everywhere. So this is what you are going to have for the allowed orbit. So this is what you are going to have, right? For the energies are just going to become the stationary states. For the energies are just going to become this. So wherever you see E squared, you just multiply by Z squared for simplicity. So this is what you are going to have, where this is nothing else but this is E naught. So that's for the energies. Now, as you can see now in this case, that the orbit in the higher Z, if this value is high, are closer to the nucleus. Those are going to be closer to the nucleus and have large negative energy values, because I mean this, if you increase this, you are also going to increase this energy value, will have higher negative value. So that will tell us that they are very close to the nucleus and have larger negative energies, and that is the electron is more tight bond to the nucleus. Now let us also do the example 6.9 to make sense of what we are doing. Now calculate the two longest wavelengths of the Balmer series of a triple ionized beryllium Z is equals to 4. Now in this case, the radiation of the Balmer series, I think you still remember the N for the Balmer series is just n is equals to 2. And so the two longest wavelengths are radiation corresponding to n is equals to 3, and n is equals to n is equals to 3, and n is equals to 2, and n is equals to 4. These two wavelengths, and n is equals to 4. Now the energies of the radiation and the corresponding wavelength are as follows. Now from E3 minus E2 minus E2 is just going to give us this value. Now from the energy, we know from the energy we can be able to get the wavelength, because we can just use this equation. Now this is what you are going to have for the wavelength. Now for the other part, for E4 minus E2, E4 minus E2, the E4 minus E2, this is what you are going to have. Now for the energy is given by this. Now from the energy you can be able to tell what is the wavelength using this equation here, where this h is the Planck's constant. Now this is what you are going to have. Now I also want you to be able to always remember this term here. H times the speed of light is always 1240 electron volts per nanometer. So that you can always easily be able to convert the electron volts to the wavelengths, or whatever way you might be asked. So that's what you are going to have. Note that we cannot use equation 6.331 to find the wavelength, because that equation applies only to the hydrogen atom. Z is equals to 1. So good people, I would like to thank you for today's lecture. So keep well and goodbye.